Okay, students, let's do some more problems. All right, we're on chapter 24. Oh man, come on now. Chapter 24, and we are on page 8. Well, I was there, and then I flipped, and okay. 873. All right, so let's look at number 13. All right, we have a solenoid used to produce some magnetic fields for research purposes, which is 2 meters long. So here's our solenoid. Yeah, I know, that doesn't look that great, okay, and it is 2 meters long, okay. And it has a radius of 30 centimeters, which is 0.3 meters, okay? And the number of turns that it has is 1,000 turns, okay? All right. When running, the solenoid produces a field of 1 Tesla. So the magnetic field, that's B. Oh boy, I got to get used to this new format. B is 1 Tesla. Well, they've updated our computers and to the new Microsoft, and anyway. All right. So it has a magnetic field of 1 Tesla. Given this, how large a current does it carry? So we want to find the current, okay? Question mark. All right, now basically what we're going to do is we're going to use a variation of the Biot-Savart law. So Biot-Savart law. So we're going to take this equation. The magnetic field is equal to the magnetic permeability constant mu naught. Please don't confuse that with magnetic dipole moment. All right, that's mu naught, not mu. So please don't get those two confused. That's the permeability constant, or the magnetic permeability constant, times the current times the number of turns divided by the length of the solenoid. Okay, now let's define what the magnetic permeability constant is, and there's a couple of ways you can write it. You can write it 4 pi times 10 to the negative 7th, and that's Tesla meters per amp. You can write it that way, okay? You can write it that way, or you can write it this way: mu naught is equal to 1.26 times 10 to the negative 6th Tesla meters per amp, okay? And you say, where in the world did you get that? Okay, if you take 4 times pi times 1 times 10 to the negative 7th, you will get 1.26 to the negative 6. So whichever one you want to use, doesn't matter, you're going to get the same answer, okay? So now let's just solve this for current. It's actually a really simple calculation. So we got the magnetic field times the length divided by mu naught times the number of turns, okay? All right, so now let's just plug everything in. So we got 1 Tesla times 2 meters, which is the length, divided by 1.26 times 10 to the negative 6th Tesla meters per amp, okay, times the number of turns, which is 1,000, and let's see what we get, okay? So let's see what we get here. So let's take our calculator, and we got 1 times 2 meters, of course, which is 2, divided by 1.26 to the negative 6th times 1,000. Close our parentheses. And what do we get? We should get 1587.3, so that's 1587.3 amps, or we could just round this up and we could say we get, you could write it this way, what did I say that was? We could say 1.59 times what? Times 10 to the 4th. All right, am I reading that right? I'm sorry. 10 to the 3rd amps. Yeah, 1, 2, 3. There we go. Or we could say 1.6 kiloamps. Okay? All right, so there's your answer right there for number 13. Okay? Let's go to the next slide. All right? Let's look now at problem number 23. Problem number 23. Okay. All right. so problem 23 says an electron moves with a speed. All right, so this is number 23 on page 874. Okay, page 874. All right. It says an electron moves with a speed of 1 times 10 to the 7th meters per second. So you've got an electron here, and let's just do it this way. Instead of doing it like that, let's just do it like this. Okay. So we're just going to say an electron, and it's moving with a speed, and its velocity is 1 times 10 to the 7th meters per second. That's moving on, isn't it? In the direction shown in figure 24.23 and 24.23, well, basically what you have drawn is you have the axis like this, and then you have axis coming through here like this. This is the y-axis, and of course that's positive. That's the z-axis, and this is the x-axis. And those are all positive. Of course, over here is the negative, okay, axis. So this would be negative x, and this would be negative z, and this would be negative y axis, okay? All right, now, and so it's moving this way. It's moving this way. That's the velocity of it, okay? And the electron, I think they have it drawn like this, with a minus sign in a circle. And the magnetic field is in the positive x-axis like this, okay? And the magnetic field is what? 0.5 Tesla, 0.5 Tesla, okay? All right, and points in the positive. For each, what is the magnetic force on the electron? Give your answers as a magnitude and a direction, okay? All right, so we want to find what? Now, we want to find what is the magnitude of, for each, what is the magnetic force, not magnetic field, on the electron. So basically, we're looking for this right here. So we're trying to, and I always like to put a B on my force. That lets us know it's the magnetic force, which is equal to the absolute value of the charge times the velocity of the charge times the magnetic field times sine of what? Sine of alpha or sine of theta. I'll just use what the textbook used, sine of alpha or theta. It doesn't matter what Greek symbol you use for the angle. Okay, your book uses theta. Okay, now, all right, so let's find it now. Let's find it for, and it says for what? For each direction? Yeah, for each direction, okay. So let's look first in the 90-degree angle. So A, so we've got the magnetic force is equal to the charge. What is the charge of an electron? Now it's the absolute value, so we're going to make it positive. So it's 1.6 times 10 to the negative 19th coulombs, all right? And then times the velocity. We were given the velocity, which is 1 times 10 to the 7th meters per second. And then the magnetic field is 0.5 Tesla, okay? And so we should get an answer of what? Well, let's see here. What do we get? All right, so we got 1.6 to the negative 19th times 1 to the 7th times 0.5. Oh, and I forgot something, didn't I? I sure did. I forgot sine of alpha, didn't I? So let me go in here and fix that. I'm sorry. Okay, well, I actually kind of took it for granted. All right, what is the angle? Well, it's the sine of 90 degrees, isn't it? Yeah. All right. All right. Okay. Sine of 90 is 1, so we should get an answer of what? We get 8 times 10 to the negative 13th newtons. All right. Now, okay, now if we use the right-hand rule for forces, we find that the direction of the force is in the positive z direction or up. So on the electron, the force is in the what? Now that, remember, right-hand rule is for a proton, for a positive charge. So since this is the electron, then the the force is, the magnetic force on the electron is in the negative z direction or down, okay? So this one is in the negative z direction, or we could just say down, right? Because you remember now, right-hand rule is for a positive charge, for a proton, okay? But when you take an electron, you have to flip everything. So whatever it is for the proton, if it's an electron, you just flip it 180 degrees, right? You just flip it over, right? So it's in the negative z direction or down. Now, all right, so if we look at this, the magnitude of the magnetic force, of course, is 8 times 10 to the newtons, okay? And so if we look then using the right-hand rule for forces, we find that the direction of the force is in the what? Positive YZ direction. So on the electron, the force is in the negative, or is in the Y minus Z plane, which is 45 degrees clockwise from the negative Z direction, okay? So please understand what we're trying to say. And it's hard for me, I'd have to be in the classroom for you to actually be able to see what I'm talking about, okay? All right, but that's what it would be, okay? Okay, because if we're in the classroom, I could demonstrate with my hand, but you can't see my hand on here, all right? Okay, all right. Let's move to another problem. Let's look at number 33. So number 33. All right. When a magnetic field strength and direction, what magnetic field strength and direction will levitate the 2-gauge wire in figure 24.33. All right, so basically what we have here is we've got a wire, okay, like this, and it is 2-gauge, okay. Excuse me, not 2-gauge, it's 2 grams. I'm sorry. Okay, it's a 2-gram wire. So the mass of the wire is 2 grams, okay? And the current on the wire, according to the diagram, is 1.5 amps, okay? And it says, what magnetic field strength and direction will levitate the 2-gram wire in the figure, okay? All right, well, the magnetic field is in this region. We're just going to do this right here. It's like this right here. I'm just going to do a dotted line, and this is the magnetic field. And from here to here is 10 centimeters, which would be 0.1 meters, okay? All right, so that's the region of the magnetic field, okay? So let's look now how we're going to determine this, how we're going to calculate this, okay? Well, this actually goes back to another equation when we're looking at a current-carrying wire, a wire that's carrying a current in a magnetic field. We can use this equation right here that the force, and again, that's magnetic force, okay? All right, is equal to what? The current times the length of the wire times the magnetic field of the wire. Now, does it tell us the strength of the magnetic field? No, because that's what it's wanting to calculate. Duh, listen to the problem. So we've got to find what? We're looking for the magnetic field strength, aren't we? Okay. So using this equation here, this is for a current carrying wire, a wire carrying a current, find the magnetic force times the current times the length of the wire times the magnetic field. So solve for magnetic field. So we say B is equal to what? Well, that would be the force divided by what? That would be the force divided by, divided by the current times the length. Okay, now we can actually relate the magnetic force to the force of gravity, because notice we are levitating the wire. So in other words, they basically equal each other, okay? So the magnetic force is going to be equal to the gravitational force. Does everybody understand what I'm saying? Because look, the magnetic force is causing the wire to do this, okay? That's the magnetic force. Well, what about gravitational force? Well, the gravitational force, mg, is pulling down. So they are levitating. So in other words, they are equal to each other. So in this equation, now notice I said in this problem, we can say this right here, they're equal, that the force of the magnetic field is equal to the force of gravity, okay? All right, so let's substitute. What is the force of gravity? Well, it's actually the weight, F of G, which is weight, which is equal to mg. So we say the mass times gravity divided by the current times the length. Okay? So let's come over here and we say then the magnetic field is equal to what? Well, it's 2 grams, but now remember, we got to put that in kilograms. So 2 grams is going to be how many kilograms? Well, let's see. The mass is 2 grams. And a kilogram is 1,000 grams, so that's going to be what? Move the decimal. So that's going to be, we move the decimal 3 places to the left, and so that's going to be 2 times 10 to the negative 3 kilograms, isn't it? It sure is. So 2 times 10 to the negative 3 kilograms. So let's plug all that in. So let's go right here, and so we got 2 times 10 to the negative 3 kilograms times 9.8, we know gravity, meters per second squared, and you should have already written that down. Gravity is 9.8 meters per second squared, okay. Divided by, well, the current was 1.5 amps, and the length is what? The length is 10 centimeters, is that correct? Yes, 10 centimeters, which is 0.1 meter, okay? All right, so let's do the calculations here. So we got 2 to the negative 3 times what? 9.8. And then we divide that by what? 1.5 times 0.1. And what do we get? Well, we get, it seems like I've done something wrong. All right, let me calculate that again. All right, so we got 2 to the negative 3 times 9.8. And then divide that by 1.5 times 0.1. 1.5. My calculator's not working. I could have sworn I typed in 1.5. 0.1. Okay. And so we get 0.13. We get what? We get 0.13 Tesla. Everything cancels out. Meters cancel out, your amps, kilograms. Well, actually, a kilogram meter per second squared times an amp meter is a what? We get a Tesla, okay? We get a Tesla. So there's your answer, 0.13 Tesla is the strength of the magnetic field to cause that wire to levitate, okay, in the gravitational field, okay? All right. Okay. All right, let's do another problem now. I think we got one more. Yeah, I think number 38 is on the same page. Yeah, number 38. Okay. Let's go to a new slide. Boy, this, man, I may change my slide format. I don't know if I like this or not. All right. Okay, let's look at number 38. So this is number 38 on same page 875. Okay. All right, we got a current loop and a motor has an area of 0.85 centimeters squared. Okay. So you got a current loop. All right, and let me see if I can do this again. So you got a current loop and a motor, and just pretend that's in a motor. All right, there's your motor. Wire coming out. All right. Okay, so this is a motor, okay, and you got a current loop, and the current loop has an area, so the area is 0.85 centimeters, come on, pen, right, centimeters squared, that's centimeters squared. Boy, this pen don't want to write, okay, of course, I have big fingers, that doesn't help. All right, that's 0.85 centimeters, see, it quits on me, squared, okay? And it carries 240 milliamps. 240 milliamps. So the current running through it is 240 milliamps, which is 10 to the negative third, millis. In a uniform magnetic field, so the field is uniform, that always helps, is 0.62 Tesla. Okay? What is the magnitude of the maximum torque on the current loop? So we want to know what the torque is on the current loop. We want to know the magnitude of the maximum torque. So we're wanting to know maximum torque. And that's magnitude now. Notice it said magnitude, which means what? We're going to have a positive number, okay? We're going to have a positive number. All right, so if we go back to our torque equation for electric motors, And by the way, we're going to maximize the right-hand rule here by just coming to the assumption that when we look at the torque, it's going to be equal to what? Well, it's going to be equal to the current times the amperage times the magnetic field times what? Sine of theta. Now look, sine of theta. To get maximum, and all right, so to get maximum torque has to be what? Theta has to be 90 degrees, right? Because the sine of 90 is 1, and so 1 times whatever is, it's maxed out, okay? So we have to realize that it's going to be at a 90-degree angle, all right? So let's plug everything in then. So torque tau is equal to the current, which is 240 milliamps. Please learn your prefixes. I'm not going to put the scientific notation in for you every time. You need to know those, all right? 240 milliamps times what? The area. Now here we got to do a little bit of conversion, okay? Notice it's 0.85 centimeters squared. Well, first of all, we need to look, if we've got a square, all right, well, we know that 1 meter is equal to how many centimeters, right? Well, it's equal to 100 centimeters, okay? So 1 meter is equal to 100 centimeters. So we need a conversion factor, don't we? Well, 1 meter squared is equal to how many centimeters squared? 10,000, is that right? 10,000. You got 2 4 zeros, yeah. 10,000 centimeters squared. So what are you getting at, Miss Shields? All right, look, we got to convert that to meters squared, y'all. We can't throw in centimeters squared because remember, our units, our SI units are always going to be in the, we're going to use meters in our SI units, okay? We're going to use meters, we're going to use kilograms. We're dealing with force, folks, torque, momentum, energy. Everything has to be in meters, kilograms, okay? So we have to convert that, all right? So we just do some dimensional analysis here. We know that 0.85 centimeters squared, let's just do some factor labeling here. Well, we know that 1 meter squared is equal to what? 10,000 centimeters squared. And so what do we get? Well, we divide 0.85 by 10,000, what do we get? 0.85 divided by 10,000 is equal to what? 8.5 to the negative fifth, right? 8.5 times 10 to the negative fifth meters. Everybody get that? All right, and so that's what you should get, okay? So we come in here and we say 8.5 times 10 to the negative fifth meters, okay? And then, of course, that's sine of 90 degrees, which is 1. And so then the torque is equal to what? All right, well, let's see what we get here. We get 240 to the negative third, that's milliamps, times 8.5 to the negative fifth times 1 equals what? So we get, did I forget the magnetic field? Doggone it, I sure did. I'm sorry. I know some of y'all are probably yelling at me. Hey, crazy, you forgot the magnetic field. I'm getting in a hurry, so it's 0.62 Tesla. There we go. Then sine of 90, which is 1. Now let's do that. So we got 240 milliamps times what? 8.5 to the negative fifth times 0.62. And what do we get? We get 1.26 to the negative fifth. So I get 1.26 times 10 to the negative fifth, and that's Newton meters. And I know that a Newton times a meter is a joule, but folks, we're not looking at work, we are looking at torque. Okay, we are looking at torque. We're not looking at work. All right, so it's 1.26 to the negative fifth Newton meters. You could round that up since we only have 2 significant figures. There's 2 here and 2. The lowest number sig figs is 2, so you could say 1.3 times 10 to the negative fifth Newton meters, okay? So you could actually do it that way because the number is significant figures, okay? All right, I hope this helps.